transfer function in discrete domain.
You want to do what?
I think I read some document they said about you need to add more zero on your discrete transfer function. When even you transfer it directly, but you need to add some more zero in case of you have high order system.
Why would you add a zero? You don't want to add anything. So maybe you're talking about delay. Delay would add a pole at the origin. Then sometimes people do averaging. Averaging adds a 0 and -1. All of these, if you model them correctly, you can put them in your model.
Yeah.
Then people erroneously say that the PWM, for instance, is a delay, which it really isn't, but that's a discussion of another day. And maybe that's what you're talking about. But I mean, if you just have analog to digital conversion and this is your system, this has to be your actual response, because that's what the actual system is. If you somehow build a 0 in there because you build it in your analog digital conversion, then you have to put it in there. But it depends on how you're measuring. It depends on how you build the system. It depends if do you use a PT1 filter, for instance, on your current sensing. Then yes, this whole thing changes. You have to model it as well.
What I mean is some of the design of the control in discrete domains. If we use direct methods that can convert totally the same poles in zero from continuous domain to discrete domain, and then there will be simple. They don't need other methods.
They do what? They do other methods. We can talk about it and have a look at it, but that's maybe too vague for now. Okay. We can talk about it. Maybe outside of this. Okay. Anyways, so now I put like the zeros is not always good. Adding a 0 in your system changes the whole whole 0 code, right? So your poles might move totally different just because you add a 0. If you look at the road locus, it changes totally depending on your zeros. So you can't just arbitrarily add zeros. Okay. So in this case, now I have our nominal value, right? And what you see is the green one, which you cannot really see all that much. It's the rectangular one. The rectangular and the direct discrete are pretty much on top of each other. And the blue one is the sample of the real one, okay? So the blue, the purple, and the green are overlaid at this point in time. And the yellow one is the continuous current. So that's the actual current that you could measure. So, and at the sample points, you see that the purple, green, and blue are exactly on top of the yellow one, right? The Tustin, however, looks sort of like an average over the time, right? Here's the sampling time, and over this, the Tustin already, for instance, if you look at the start of it, the Tustin actually doesn't start at 0. It already starts at the average over this period. So it will not yield the exact current that you think you would have at the sampling time. It gives you the average over this time. It also starts already with the value. So at 0.0, it already thinks that the current is somewhere, which is awkward, right? Like your system cannot really jump. So it seems like it can, in energy, jump right away. You haven't even done any time yet, and it already has current. So it also already should feel a little bit not physical, or physically incorrect a little bit. But the other ones look pretty okay, right? All of them basically overlap. If we now increase the t over tau, let's do something dramatic now. Let's do 0.5. And as we saw in our figure, 0.5, we already have, and this is way too zoomed out, but at 0.5, we already have quite the gap between forward rectangular and Tustin, and the real one. But I mean, so this is basically 0.5, and direct discrete, which is basically what the system is at 0.6. So it's a little off. Well, let's see what this does. Oh, that was too short. Let's do it for, or let's do it for 3, 2. So you see now the rectangular becomes worse, right? So it doesn't match the actual one, and the purple and the blue again are overlaid, because the sample continuous and our direct discrete model are always correct. So, and the continuous now has this bow curve because the tau actually now has an influence, right? The Tustin still is like the average, and it seems pretty good as average. It's 4,000 here, and this is 8, it winds up at 8,000, so that's okay. And the rectangular starts to deviate. Okay? So far so good. So now let's do 1. What happens? Without doing the simulation, what should happen now? So we should see Tustin as a bigger error, right? That's okay. But what does the rectangular do now?
Actually more than that.
It not only has more error,
It's
but
only 0. So the pole is.
the pole is now at 0, right?
Yeah, so it should be many.
It should look like a deadbeat now,
Yeah.
right? And let's have a look at it. You see this? The rectangular already reaches the end node, and we should do this a little longer so we see that it actually reaches the settling point. Is this long enough? Yeah. See this? So the continuous domain, wherever it reaches in the end, it already has this after 1 beat. I mean, for controls that's good, but we think our model behaves like this, so that's totally wrong, right? So, our plant really is not a deadbeat plant, so it obviously moves like this. The Tustin, and the Tustin still seems okay, right? It still moves pretty much like this in an average manner. So in that case, that's usually why people say Tustin is better, but at low T over tau, I would really recommend the rectangular one, if at all. But what happens at 2? T over tau is 2.
The Tustin is
So that there's 2 really cool things happening at this point. So the Tustin is a deadbeat now, right? And what happened with the rectangular?
pole is negative.
The pole is at -1. What is -1?
A -1.
It's exactly on the line of instability, so it's literally on the verge. So what would that look like? What happens with all the poles on the left side? All the poles on the left side of the circle is forced oscillation, right? We talked about this.
Yes.
And I'll look back at the video and I actually missaid something about forced oscillation. So forced oscillation in this case is always behind the transfer function, right? So in this case we should see a forced oscillation with the frequency of our sampling, right? On top of our state. So for some reason I said you only see it in a manipulated input. That only happens when you do an NSTS, or when you do command feed forward and not thinking about it correctly. But we get to this later on. So now you should see a forced oscillation of your state, but it's still stable, right? But it's also not damped, so the amplitude shouldn't change. And what will the amplitude be of that? What do you think? What will be the amplitude? So it reaches, let's say 4 in the end, whatever the value is. What will be the amplitude? So in mean it will be correct and the amplitude will be like the whole. So let's just have a look at it. But if you're a little bit, if you think about it, you might come up with it yourself. So Tustin should reach it within 1 beat, right? So it did. It won't change anymore. But the rectangular one overshoots it by the amplitude, undershoots it by the amplitude, overshoots it by the settling point. So it never changes, it stays on this because it's literally on the verge.
Steady state.
And the mean of it is actually the correct value, but it just jumps between the magnitude, like twice once the error plus, once the error negative, 1 plus, 1 minus.
One of control.
Yes, pretty much. Like if you do a mean of this, it's perfect. Like we reach our temperature, but it's in between it's super hot and in between it's super cold. But a mean, it's okay. If tau is small enough, we're a PT1 ourselves, so it's fine. But really,
Steady state error.
it doesn't have a steady state error if you do the mean of it. So it actually has no steady state error as a mean. So if you do a mean of all the points, it would actually be the correct value. But in between it's just always good. So this is not really, I wouldn't call it a steady state error because it just never has a steady state. It always will oscillate.
How you know this one? Because sometimes we.
It's also not a control yet, right? This is just our plant. We think our plant does this by itself. It's really nothing physical, just math. Maybe you find a physical system that does this and could, but I don't think so. Yeah, but this is what we expect from these poles. Okay, so we could do the math ourselves and see what happens. Okay. Now let's get back to and we want to get some Bode plots to see if what we expect the whole system to behave like. And let's get it from. Let's get it from here. So I don't know if you've seen this. You can basically in MATLAB tell what's your input and what's your output, and basically get estimations out of it. You can get a linearized model. I'll show you different ways to do this today. Okay, so now let's do some linear analysis on this. And you can use this as a sort of a tutorial if you wish, because you will have this on video and you can basically pause how I do it. I'll send you the video. Okay, so first of all, we do the Bode plot between our input and the actual sampled continuous version, right? And I will only do this once because the direct discrete always matches. And you can play around however you want to. You won't be able to not make it look the same, unless you did your math incorrectly. Okay, so it actually doesn't plot it far enough because it doesn't know it should go to Nyquist, but it will automatically do this once I put others in here. So this is the continuous one. And now let's do the direct discrete on top of it. On top you do if you just plot it up here again, the Bode plot one, and then we should get an overlay. And the overlay is exactly on top of it as we expected it to. Now let's do the Tustin. And now it did it up until Nyquist, so we really see that blue and orange, this was real and direct discrete, they go down to this 180, right? So you see these two breaks, this is your natural frequency basic of your pole, and this is what the Nyquist does. In Tustin, this doesn't happen because we have this 0. We have a 0 at -1, and then you have a 0 plus the normal pole, and this -90, or this is actually, if this is a 0, it's plus 90, right? They cancel each other, and you don't see this effect anymore. So in Tustin, actually, the Bode plot looks totally different. And let's say rectangular, what do you expect with a rectangular? In this case, now that we have 0, 0, 0, 5, taught, T over taught, we expect it to match basically the direct discrete and the sample one, right? And it's a very good approximation if we have this kind of T over taught. Okay? So let's do something radical now. Let's do 1. Let's do 1 and start with our direct discrete. So what do we think will happen? Should look the same, right? But now the eigenvalues are closer because we use the eigenvalue moves to the left, so it's way closer to when the Nyquist stuff happens. So we don't see 2 eigenvalues now. It looks almost like 2 and 1. And you see this stagnation really way more pronounced here. And that's just because the eigenvalue is not at a different point. But it is what the system does. So just to show it to you one more time, we now use the actual continuous system at a really, really bad T over tau. And now, compared to the direct discrete, exactly the same. Okay, because it is the real solution. We didn't do approximation, this was solving the system. Now let's do Tustin. What will Tustin look like? And also again, it just goes to -90. And because of that, it goes to infinite, because the 0 has this, and that's what I plotted. I plotted the 0 instead of the pole at -90. The pole goes up, right? And the 0 goes down.
Yeah.
So that dominates really at that frequency. So it's so different now if you use Tustin. And the rectangular one, something funny happens, right? We have the deadbeat at 1. So what should we see?
Magnitude should be constant.
So the magnitude will be constant, and the phase goes from 0 to 180. So the phase does not match this perfectly anymore. It at least does the same thing, but it is different. And the magnitude stays constant. It never drops. This plot of magnitude is really poor because we have the Tustin in there, and it just makes the scaling of the y-axis bad. But it is constant. Okay, so we could now plot also for 2, but basically one becomes also deadbeat and the other one becomes something interesting. So you can have a look at it. So, okay, what else do we want to talk about? Okay. Maybe we skip this because we only have one hour left. Maybe we come back to what I want to talk about. Okay, so the control design we sort of talked about last. It's the same as we did it in the last lesson, right? So we basically can choose our poles. So I showed one version where you basically put the 0 into the pole of the plant, and then you move the integration pole to the left, right? So that's one way to do it. And let's see here. So that's the modeling. Now we go into control. So what I do here, I use different signals to test different things. I can test command tracking with this or dynamic stiffness with this. And let's tune our controllers real quick. So this is for the Tustin, and what I try to do, so now I expect a 0 to be at -1 because of the Tustin approximation, right? And I now chose a 0 somewhere close, so I have 2 poles here if I decouple the R, right? So I decouple the R at the Tustin so that I actually have 2 poles at +1 and 1 0 at -1, and I place the 0 here so that one pole moves in this direction and one moves here, but I have 2 poles. So I didn't decouple one pole. This is sort of what we did in continuous domain. We wanted 2 poles because it does something good to our dynamic stiffness, right? And we'll see this. And let's do controller. Okay, I think this should be all I need. Okay, so let's start with dynamic stiffness. And maybe first I explain the model. So up here is Tustin. First of all, this is Tustin with its controller and the approximation as we think it is. So first we test, did our pole 0 placement work if this was the actual system, right? So I have the R, I don't do parameter error right yet, but that would be here the error that I put into this game if I want to decouple the R. And then I test it to the real system. So I use the same controller, but now on the actual LS. And if the approximation is good, both of the system will yield the same thing. If not, I will maybe see, okay, I did tune it correctly for this approximation, but on the real system it doesn't work. I do expect that this will happen, because I don't think Tustin is correct. However, then I do direct discrete modeling. I didn't do it also for the rectangular. I wanted to do it also for the rectangular, but in our nominal values, they really are the same. It would be redundant to really do it. Then we have the direct model. Again, I use a different controller. Now these were 2s, and this is my plan. And I look at what happens if I put it on the real system. And they should do the same thing. If not, our direct discrete model is wrong. Always important. And then I also did the same thing with the deadbeat controller. Maybe we talk about this later. Can have a look at it. This is basically my deadbeat design, and this is the plant as we think it is. And then I also put it on the actual road. Okay? So that's basically what we're looking at. And now I do a dynamic stiffness test. So what I do is I don't do any inputs. The input is 0, and I put a chirp signal into my disturbance voltage. Okay? And what we see is, let's start with the Tustin, what it thinks it does. Hopefully the scope opens up. This is slower than I hoped it to be. Okay. Nope. Oh, I still have the long T, don't I? This will never work with that, so let's go back to the normal. Okay. Okay, so what I do is I put a chirp signal with a constant voltage on top of it. Do you know what a chirp is? It's basically a sine wave that changes the frequency over time. So people use this to also estimate transfer function. It's like a whoop, whoop, and it starts at a low frequency and goes up. If you ever see people using the signals in a room, they're doing the same thing here. They use first a low frequency, then a higher, and look at the response. And that gives you basically the transfer function.
What's the name of the plot?
Chirp. You can also use white noise, but that's a very common approach to get the system behavior. So at this, back here, and I use the logarithmic chirp, so over time it logarithmically changes. Unfortunately, this structure is really going slow. Maybe it could be the, I can't give a little, oh, there you go. Yeah, I gave him very little power so that he's very quiet. Okay, so it starts with a really low frequency, and our controller decouples it basically, right? Or it rejects the disturbance with low frequency. That's what our integration portion does. This is basically, if you draw this outline here, that's your dynamic stiffness plot. Okay? And up here, the inverse of it. Does it make sense? I give higher frequencies. At high frequencies, it rejects it, so it's our plant. At mid frequency, it's basically our peak portion, and that's our integrator, right? So that's also a way to look at dynamic stiffness. So that is what the Tustin thinks what it's doing. The real system, however, looks a little bit different. It also has this and this, but up here, not really. It's way overtuned. It has a way higher break frequency than it thinks what it does. Okay? So these two don't match, but I still separated the two eigenvalues, so I have an integrative portion of my dynamic stiffness. In the direct discrete right now, I used a control strategy that decouples, or that put the pole on top of the zero on top of the pole of the plant, and now I only have one pole. So we should expect that we don't have high dynamic stiffness at zero frequency anymore, right? And that's what we see here. So I did put the eigenvalues to 300 Hertz, and if we zoom in here, you will see that when the we see a little bit maybe later, you see that we get the frequency. Wait, this is what it thinks what it's doing, and now let's look at the real thing. You see that it looks exactly the same. You can't tell right now that it's exactly the same, but you see that we do have this behavior also in the real system here. So we do hit the eigenvalues correctly, but because we cancel the poles, we don't have this V shape anymore, right? And we don't have to. That was just the easiest way to do it. We can also do two poles if we want to. I hope I have hit the right one. Now I redesigned the control a little bit, and now I use direct discrete to get two poles in there. And now we should see similar behavior. We also now rejected low frequencies and get the same shape. Okay? And a lot of people will tell you decouple the pole of the plant. And I'll tell you, maybe. It's not always the best idea. Because now we have way more dynamic stiffness at low frequencies, right? So you can choose, okay? You can choose where your poles are. Design them whatever you think is important for you. If you don't really have disturbances at low frequencies, maybe you don't need the second pole. But if you do, you probably only get high dynamic stiffness with this. Okay? And we can also look at command tracking. So if I get rid of the disturbance and I do the same thing now, also a chirp into our command, we should also see a nice command tracking result. Okay, so my chirp now has a height of 10, or a magnitude of 10, and I reach the mag, and I reach it, and as the frequency goes up, at some point I don't reach it anymore, right? That's because I'm above my bandwidth. And you should have seen a little bit of this also in the continuous limit. It depends on how far you separate your eigenvalues and what happens around the bandwidth. And now, let's see where we hit our bandwidth. What should be the value of the magnitude at our bandwidth?
It's 1 over square root of 2 times.
It's roughly 7.
Sometimes. 20%.
It's around in that ballpark here. You will see weird things that you don't have in continuous domain. And if you look at the whole thing, the magnitude is not always correct, but that's also because certain multiples of your t will make the sine wave basically go away. So you don't get a clean plot. So we get 182, and I think I set it to 177, so it's like really, really close. But you can basically get really good estimations of eigenvalue placement with this. And let's put them side by side. So that's what the direct discrete thinks what it's doing. Oops. So yeah, 27 was what it thinks it's doing, and this what the 24 would be what the real one is, and if you put them side by side, you see that they really do the same thing, okay, for command tracking. However, if you now compare it to what Tustin is doing, this is what it thinks it does, and this is what the control actually does. So your eigenvalues really wind up somewhere else. You see how dramatically different they are? So I'm not saying you don't get a working control here. It obviously works, right? It also has dynamic stiffness at low frequencies, and the command tracking is okay. But it really is not where you want it to be. Your eigenvalues could be anywhere. And that especially is a problem when you do, for instance, cascaded control, right? You need to have your eigenvalues somewhere. If they're just like totally off, then you will have a problem. Okay. So that's all homework 3. We could talk about this probably for hours. But I also have to teach you a couple of things real quick, so you can also do homework 4 as a final thing. But if you get all of this right, you already know a lot about current control and discrete control. But we want to get a couple tweaks here. We want to, for the whole converter, we also have to do the cascade control, right? So we have to look today how to do cascade control, and we want to have a look at observers and feed forward and DID. And then you basically are really have a good foundation, at least for now. Okay? So for that we have to go back to the table. And if you want to, we can also talk about this homework after the class. Oh, this actually does not pick up the whole board. It could be a problem. Hi. Could you go one to the right? I actually didn't get the whole board. It's a little bit unfortunate. So right now, I can only draw until here. Okay. So let's start with an observer. What do you think the observer should look like? when we do a Lumber observer? How would we start? So what does an observer need? What's the general structure?
We have the equivalent model for the plant.
We have a model of a plant. And what does it also need? So we have a model of a plant. That's what? That's our NSDLC, right?
The input to sense.
Sorry?
Create inputs from the sensors.
Yeah, so we get the actual current sensor, exactly. The input of the state that we observe.
Then we have feed forward from the reference and we do some controls over that.
Okay, so a Lumber observer, basically, you're absolutely right. So it will have the NSDLC hat, right? Because we never know this perfectly. And we have a state. Let's use example 2.